You know variables, you know loops, but when you sit down to write a program, you don't know where to start. This is the screencast for you. This is Blank Editor. Welcome to Blank Editor, I'm Al Swigert. In this episode, we're going to be solving problem 3 on projecteuler.net. Now in this problem, we want to find the largest prime factor of this monstrously huge number. Now there's a lot of math concepts that go into there that you might not be familiar with, but that's not something to be afraid of. You can always just Google for something. For example, what is a factor? You might want to specify that you're referring to math when you're talking about factors. And you'll find a lot of information about this. But basically, a factor is just the numbers that you can multiply to get the number that you're trying to find the factors of. So say I want to find the factors of 24. Some factors of that might be 12 and 2, because 12 times 2 equals 24. But they could also be 4 and 6, and they could also be 24 and 1. So 1, 24, 2, 12, 6, 4, those are all factors of 24. Now something pretty interesting about this is, let's take these two factors, 2 and 12. You can then, in turn, try to find the factors of 12. Say that would be 2 times 6 would equal 12. And then if you take the factors of 6, that's just 2 times 3, until you can finally get no other factors. You can't break it down anymore. And these are prime numbers. These are numbers where their only factors are themselves and 1. So the only way that you can multiply two numbers to get 3 is if you multiply 3 and 1. So 24 is not a prime number because you can multiply other numbers besides 24 and 1 to get it. So that's what they mean by factors, and in particular prime factors. And what this Project Euler problem wants us to solve is getting the largest prime factor of a particular number. So in 24's case, it would be 3. So let's think about what we need to do in this program. Well, we need some way of getting the factors of a number. Not only that, we have to figure out if they're prime numbers or not. So we need a way of determine if a number is prime. And then finally, once we have a whole bunch of prime factors of a particular number, then we need to find the highest prime factor number of all of those. So find the highest number, and that'll be the final answer that Project Euler is asking us for. So let's break this down. We can probably section this code off into a couple functions. Say we want maybe a getFactors function, and this will accept some number that we want to find the factors of, and then return some type of list maybe. I'll just put a blank list right there for right now. And we'll worry about this other stuff later. So let's think about how can we get the factors of a number. Now, if you don't know how to do this, well, you can always just go to Google and ask how to find factors. Yeah, Python. And I'm just going to open up the first 3 tabs that I find and just sort of scan through all of these. And here's a solution that's in one line and just crammed full of functionality into that one line. It's not really readable code, unfortunately. I'm going to see if there's some other way that I can figure this out. Now in this second result, you can see, oh, this is really simple. So factors of a number n are all the numbers that evenly divide into it evenly. Okay, so I is a factor of n if n mod I equals 0. Let's check, is that actually true? So 24, let's see, one of its factors was 6. So I'm going to see if 24 mod 6 is 0, and it is. How about all the other factors that we had? 24 and 12, 24 and 2, 24 and 1. Well, of course, 1 is 1, and the number itself are always going to be factors of them. So yeah, this seems to be correct. Let's give some negative cases as well. So the number 9 is definitely not a factor of 24, so this should not be 0. And that's true. Okay, so that seems to actually work. let's go through, I don't know, sort of all the numbers from 1 up to this number, and then see which ones have a result of 0 when we mod the number in that range. So we'll just start with 1, and then we'll move on to 2, and then move on to 3, and then 4. Maybe go one more. Okay, so if we do this, we can see that yes, 1 is a factor of 24, 2 is a factor, 3 is a factor, because all of these are 0, and then 5 is not a factor. So we'll just save all of the factors to a list. Let's say factors equals a blank list, and then we'll just loop. I really dislike using single letter numbers, but so let's not call this in. We already used number here. Let's call this potential factor. We'll be going from 1 up to the number and including that number. So now let's just check if potential factor, the original number, if we can mod it by this potential factor, and that results in 0, then we know that that potential factor is in fact a factor. So I guess if number mod potential factor, and if that's 0, then potential factor is a factor of that. So we'll just get our factors list and append potential factor to it. And once we've iterated over this full range of numbers, we should be able to just look at that list. So let me try this out actually. Now, I don't want to do print debugging. That is the impure way of producing logging messages. You should use the Python logging module instead. It just requires 2 lines of setup. You're going to want to display the debug level of log messages. So now we can just have logging.debug, and let's just test this out, say on 24. And I'll run this and see what it produces. So that returns, yeah, this looks right. So the factors of 24 are 1, 2, 3, 4, 6, 8, 12, 24. That seems to work. That's great. Okay, next, we want to figure out which of these factors are going to be prime numbers. So we're going to, in order to do that, we're going to need some way of determining if a number is prime or not. I'm going to go ahead and create a function, isPrime, and this will return a Boolean true or false, depending on if this parameter is a prime number or not. Now, a prime number will only have itself and the number 1 as a factor, so if we loop through a whole range of numbers, kind of like what we did here, we can just keep seeing, if they have any factors or not, other than 1 or 24. Wait a second, we already wrote code just like that. In fact, we could just use this getFactors number. If we pass a prime number to getFactors, something like 17, then getFactors will only return a list of 1 and the number itself, so 1 and 17. Is that true? Oh, I made a slight typo here. This isn't syntactically correct Python code, because Python's expecting some code after this def statement. We can't just leave it hanging with nothing out there. So I'm going to use the pass statement, which is exactly for this case. If we just need to have some code that does absolutely nothing, but for reasons of syntax, it has to be there for Python to think, okay, yeah, there's something inside this def statement. So let me try running this again. Yeah, getFactors for 17 just returns 1 and 17. So really, all isPrime has to do is just call that getFactors function and pass it that number, and then check if the length of that list that it returns is 2 or not. So yeah, so if it has 2 factors for this number, the length of that list is 2, then that number is prime, so we should return true. And if not, then it'll return false. So let me test this out as well. Logging.debug. Let's say, so 24 is not prime. So I'm going to use string formatting here just to put this value, this integer, or this Boolean value from isPrime into a string. So if you're not familiar with this, this %s just means insert a value, the first value in this tuple that follows after the percent sign after this string right here. It's basically a nicer way, instead of doing string concatenation, where you would have to then convert everything into a string, and that can be quite a headache, especially if you have multiple %s's in here. Anyway, then we'll also check this out on 17, which we do know is prime. Yep, so that function seems to work. Now we're playing pretty fast and loose with the testing here. I mean, there could be all sorts of cases that we're not testing, but we're just going to go through this small, simple problem. Alright, now we can get the factors of some number. We need to go through all of those numbers and determine if they're prime or not. So let's go back to the problem. It wanted us to check all the factors of this number. So I'm going to call get factors on that big number 600 million something. I'll just store that in a list called all factors. And then, let's see, for each factor in all factors, if that each factor, that's probably a mouthful, I can just get away with calling them factor. So if the factor is prime, then what? Well, we just need to keep track of the largest prime factor. So maybe I'll just create a variable largest prime factor. I'll set that as 0. And then whenever we've found a prime factor and that factor is bigger than the previous largest prime factor we found, then we'll just update that largest prime factor variable to be equal to factor. So by the time we iterate through all of those factors, largest prime factor should have the very largest prime. Yeah, the largest one and the prime factor. Whoops, forgot to connect these together. We needed to have a AND operator in between them. So it's checking, is the factor prime? And if so, this will return true. And is that factor largest than the previous largest prime factor? So if those are both true, then we update largest prime factor. So this is all our finding the highest number code. And then once that's finished, we should have the entire program finished. So let's go ahead and just run this code. Yeah, well, this seems to be taking a while. In fact, it's not even really... That's worrisome. Let's think about this code. I mean, this is a pretty big number, 600 million. And if we go into our get factors code right here, we can see that, oh yeah, we're going over the entire range from 1 to that number. So this is going to be 600 million when we call get factors with that 600 million number right here. So that's going to take a long time. Way longer than we want to spend. So let's think about how we can make this, which seems to be our bottleneck, a bit faster. Well, I mean, technically, we don't have to go over the entire range. Like, remember the factors of 24 were just 1 and 24, and 2 and 12, and 3 and 8. I mean, really, if we can figure out that 2 divides 24 evenly, well, 24 divided by 2 is 12, so we can calculate the other number in this pair of factors. So we don't have to go all the way through all 24 numbers, we can just go through half of them. So what if we just divided this by 2, and then this is going to be a float, so I need to convert that to an integer, because the range function only accepts integers for their arguments, not floating point values. So that cuts that time in half. Is that really going to be fast enough, though? I mean, that's still going to be 300 million. I'm going to just run this and see. Yeah, it's still taking a while. Okay, let's cut that out. Let's see if Google can help us out with this. Let's Google for how to efficiently find factors. Oh, how to find factors of a number efficiently. And let's just add Python to the end of that too. So if we just open up the first couple of these, and we'll find in one of these answers, the person tells us, actually we only have to go up to the square root of that number. And it goes on to explain why, too. So say we're finding all of the factors up to 24. Well, really, if we import the math function so we can get the math module so that we can get the square root function. We look at the square root of 24, it's 4 and some change. So, I mean, 5 times 5 is going to be greater than 24. So any factor that's above, that's 5 or above, basically any integer that's larger than this number, it's going to be the pair of some integer that's smaller than this number as well. That seems true, like 24 divided by 4, its pair is 6. We don't actually have to go all the way up to 12, we only have to go up to the square root. So let's think about all those factors that we've seen before of 24. There's 1, 2, 3, and 4, and then 4's pair is 6, and then the pair of 3 is 8, the pair of 2 is 12, the pair of 1 was 24. So these are all the factors of 24. You can notice that the pairs begin after that square root number, so it's only after 4.89. So we can change this code around. We'll go ahead and import the math module as well. And we'll just go up to the square root of our number. Plus 1, because we also want to include the square root number itself. Now this is much better, because even though a number like 600 million is super huge, if we look at the square root of 600 million, well, it's only about 700,000, which really isn't that much. It's less than a million. I mean, my laptop can probably handle that, but let's go ahead and run this just to find out. We still haven't tested this code technically, so I don't know if this program will work. But let's see if this can actually at least get an answer within a reasonable amount of time. And whoops! We've gotten an error message, and error messages always look really scary and complicated if you're a beginner in Python, but let's just look at this rationally. Let's see, here in line 8 of our code, which is this for loop, it's that same line that we've just modified. That makes sense because it was working before we changed this line. It's going to say that float object cannot be interpreted as an integer. Now you can just go ahead and copy and paste this into Google to sort of figure out what that means. And just open up the first few links and look through them. And if you do that, you'll find that actually the error is caused because math.squareRoot is returning a floating point value, which the range function does not like to accept as an argument to itself. So I'm going to just change this to an integer by passing it to int. Then we'll be adding that 1 there. So let's try this one more time. Whoa! I can't believe that just went through that so quickly. Well, I just pressed the key and now it's done. That is much better than what we had before. So let's see. 486,847. I mean, what's being printed out here is the largest prime factor. So let's check. Is that the actual answer to our problem? And no, it doesn't look like it. Let's go back to our code right here. Let's look at our debug statements. Getting the factors of 17 right here. We find that, oh, that's just producing 1, but it should be 1 and 17. That's because, oh, we're only adding that first number of the pair, that first factor of the pair of factors. Remember, we also need to add the other number, and that's going to be the number divided by that potential factor, which at this point we've already shown to be a real factor of it. But let's think about this logic. I'm going to pull this off to the side right now. So if we have a number like 17, we're testing that 1 is a factor of it, we're going to find that, yep, 1 is a factor of that, so we're going to add this number 1, which if we look right here, is that potential factor, just this number right here. But more than that, we also want to find that number divided by the potential factor. And we're going to use integer division just to make sure that we get an integer for it. So that's going to be 17. And we also want to add this number as the pair factor to our first factor. And so that's why we're adding this to our factors list. Okay, now we're going to get a complete list of factors. Let's run this one more time. We can see, yep, we're getting 1n17, and then we're getting the number 6,857. Is that the right number? Yep. So in this episode, we've gone through and done a little bit of math, but not too much. We just learned about factors and prime numbers. Turns out that calculating if a number is prime is pretty simple given the code that we've already written right here. We use the mod operator to figure out if a number is a factor of another number or not. And then we went back and then, after doing a little bit of research, realized that we can vastly improve the efficiency of our program by just going up to the square root of our number instead of going across the entire range up to that number. And that's really important once we get to very large numbers like 600 million right here. So I hope you found this episode useful. I'll see you next time.